We're going to start 8.2. The last thing we're going to do, we did 8.1 with Gauss-Jordan elimination. Some of you need to be practicing that more. Others of you have gotten it. Then we do 8.2 today, tomorrow. We're going to start a review on Wednesday when I'm still here. You'll review Wednesday and Thursday, and you'll have your test on Friday. I will not be here Thursday and Friday. So on Thursday, I will have the book out. More than this. It'll be laying on the desk where you guys can check your answers to odds and evens so you know whether you're right. Okay, so you need to pace yourself. So maybe you're working on things you don't really understand on Wednesday during class so you can get help, things like that. Got it? So today we're going to be adding, subtracting, multiplying matrices. Fun stuff. There's just a few rules that apply to it. Okay, so again, I'm going to just remind you that when we name matrices, we have a matrix. We've done that before, right? We just had all the numbers. That's a matrix. Well, we can also name it with a capital letter, just an A. Okay. We can also name it a little a with a sub ij. Can anybody guess what the I and J would be?
The row and column.
Number of rows and columns. So if I had A sub 3, 4, it would be a 3 by 4 matrix. Okay? We typically name matrices with that capital letter. I mean, I'm not writing the whole matrix unless I have to, are you? Probably not. Okay, so that was just a reminder of that. Okay, two matrices are equal if their corresponding entries are equal. So everything in every place has to correspond, right? So I said the matrix on the left is equal to the matrix on the right. So that means 16 has to equal 16 because it's the first row, first column, right? So what does that mean 5 equals? 2x plus 1. So 5 equals 2x plus 1. Could I solve for x? Yeah. I would subtract 1. And so x would be what? 2. And if I plug it back in there, 2 times 2 is 4 plus 1 is 5. Okay, so what does 3y minus 5 equal? 4, because it's in the third row, second column, right? So you have 4 equals 3y minus 5. Add 5. And so y is 3. Pretty basic, right? It's one of those duh ones. If this matrix equals this matrix, everything in the matrix has to equal each other, correct? If I had, oh, we have another x there. Okay. What?
It would be the same.
It should be the same, right? It should come out to be 2. So you had 6 equals 3x, so x equals 2. And so if I put in 2, I get 6, and we're good. Make sense? Questions on that, guys? If I put a -4 here, would that be a true statement? No. If one thing is off, it's not equal. Okay? Am I good? Haley, am I good?
Yeah.
So matrix addition. You add corresponding elements. In bold underneath it, it says addition of matrices, and I'm going to say subtraction, okay? Addition, subtraction, same thing, okay? Addition, subtraction of matrices of different sizes, order, shape. That means they don't have the same dimensions, correct? Is not defined, or it's undefined, meaning you can't do it. So if I ask you to take a 3 by 4 they'll catch up. Oh, wait, no. Thanks. If I ask you to do a 3 by 4 plus a 5 by 6, your answer would be what? Undefined. And you would love that and you'd walk away, right? Are you going to get a bunch of those? No, but are you going to get a couple of them? Yeah. You need to know when you can and when you can't do it. So if I have A plus B, I just add them. So A plus B. So that'd be 2 plus what?
0.
Oh, can I do it?
No.
I can't do it. That's nice. Okay, so if I say I can't do it, like that, this right here shows me why I can't do it, right? My size. Does this right here show me why I can't do it?
No.
No. So I'd have to do A plus B, and A is a what?
3 by 3.
A 3 by 3 plus
3 by 3.
a 3 by 2. And so you would then put undefined. Some people go, well, I can add the first 2 columns. No, you can't do it. What?
You can tell, like, they're different.
But did I explain why I couldn't do it by putting their dimensions?
Yeah.
Yes. So when I say explain, that's all I want. You can never put undefined, no solution, infinitely many solutions without an explanation why. So well, I didn't add any, evidently. Oh, I can add these. Sorry. We didn't do this one, did we? I was like, we have to have an addition one. Okay, so I'm just going to call this A and this B. So A plus B. If they have to be the same size to do, when your answer is going to be the same size also, right? So my answer is going to be a 2 by 2. So I'm going to have -1 plus what?
1,
1 is
0,
0. And 2 plus 3 is,
5,
and 0 plus -1,
negative 1,
and 1 plus 2.
3.
So there's my answer. What if I want A minus B?
You have to do
So
Just
this
find
right
out.
here
one
would be a
minus
minus. So the easiest thing to do would be distribute that negative in, wouldn't it? Does that make sense?
Mhm.
Distribute the negative and then just add them. So if I distribute that negative in, I get a -1, a -3, a +1, and a -2, right? Everyone see what I just did?
Mhm.
Okay, so now I have -1 and -1. Once I distribute it, it turns to a positive, correct? Mm-hmm. So -1 and -1 is
Negative 2.
-2. And 2 minus 3,
Negative 1.
-1. And 0 plus 1, 1. And 1 minus 2, -1. So when I add polynomials, I just combine like terms, yes? If I had 2 polynomials, 6 terms, 7 terms, whatever, I just add them, combine like terms, right? When I subtract polynomials, what do I have to do with the negative before I start? I have to distribute it. Did I have to distribute this negative before I started also?
Yes.
Yes. Many of the rules. Now close it. Thank you. Many of the rules with matrices are the same as with real numbers. The only difference is we don't divide matrices ever. We can't. There's no operation that allows us to do that. Okay, so what we did here is we distributed the negative. So that leads us to our next slide. It says if I have a -3 here, that's called a scalar. Okay? And the other one I had a -1, didn't I? Yeah, by doing the subtraction, I had a -1. Yes.
You have to write all this?
That's up to you. You need to know what a scalar is. Okay, you could paraphrase. So if I have -3 times this matrix, I'm going to scale that matrix. When you have a 2 out in front of a polynomial, that 2 is called a scalar also because it increases every value in there by 2. Just don't ever tell you that. So with scalar multiplication, what do my little arrows show me I'm just doing with this -3?
Distributing.
I'm just distributing it. Did we just do that when we subtracted those 2 matrices?
Yeah.
So do you subtract everything by 3 or multiply everything?
You're multiplying everything because it's right up here. You're multiplying everything by -3. Gotta check how far we need to go, guys, because I don't want to go too far. Actually, if we go too far, then you can have more time tomorrow, I guess. Okay, we're still good. Okay, so then the next one is just in words what we did on the other slide. Remember when I took, I took A minus B, correct? But this would be like B minus A. That this right here, what is my scalar? Negative what? 1. And that just shows you it's really just -1 times A. Just exactly like if I did this with some random polynomial. Is there a -1 right here?
Yeah.
Same exact thing. I'm really trying to get you guys to realize that this stuff is no different. Okay. Order of operations in matrix expressions is similar to real numbers. If you have, what does this mean to do?
Sure.
Square it. So once you know how to multiply matrices, you would multiply matrix A by matrix A, correct? Okay. So if I had 2A minus 6C. And what I like to do is on the test especially, I'll give you like 5 matrices up at the top, A, B, C, D, E, or whatever. And then I'll give you different things at the bottom where you use those same 5 matrices. Make sense? Okay, so what does this say to do? 2A minus 6C.
Like 2 times A and then -6 times C.
And then combine the 2. Okay? So everything in matrix A times 2, everything in matrix C times -6, and then bring them together. Now, this only works if matrix A and matrix C are what?
Same shape.
Order.
Equal order, size, dimension, whatever you want to say, right? If I can't subtract them because they're not the same order, can I still multiply them by 2 and 6? Yes.
Yeah.
So you would still do the multiplication of 2 and -6 because that operation I can do, correct? And then when I get to the subtraction, I can't do it. Then I would say at that point it's undefined. So, but point being is, did I multiply first before I did my addition subtraction?
Yes.
Yes. Okay, now let's get to some fun. Okay, what's A say to do? Well, first of all, write A and B on your paper. I'll give you a second.
Turn off the light.
Sure.
Please. No. Thank you.
Those clouds help, but they don't help enough. Okay, do we got A and B written down? What does example A say to find?
times.
3 times it. So it tells me to do 3 times. So what am I going to get going down?
6. -9. 6.
Okay, you guys do the next one.
Okay, so we're not gonna add A and B afterwards when we do it?
Nope, this one just says 3A.
Okay.
That's all it says. Okay, so your next column, did you get 603? And your next column, 12, -36. Okay. What does example B say to do?
-1 times.
Negative matrix B. So that means everything in matrix B, I'm going to multiply it by a negative what?
1.
1.
Can you just like switch the signs?
Mhm. Well, that would be multiplying by a negative 1. So I get -2, -1, 1, 0, 4, -3, 0, -3, -2. Do these go kind of quick?
Yeah.
Yep.
And then you just combine those.
And this one on C, they actually, this C, I just put it, so I'm using the first 2 things I did.
And then you just like add them?
Because I already multiplied, this is a horrible matrix sign, right? I'm sorry, guys. Since I already took negative B, I don't have to do it again, do I? No. So now you're just going to take 3A and combine it here. I'll give you a second to do that. Okay, so did you get by column 4, -10, 7, 6, 4, 0, 12, -6, 4?
How did you get -6?
-3 and -3. Did you put 0?
I didn't see that -1.
It's 6 minus -2 is 4.
No, it's 6 minus 2. We already took,
Oh,
since we already took the negative, it's essentially an addition. When I do these problems, I always distribute my negative and turn it into an addition, because then you're not trying to distribute and combine at the same time. You'll make less mistakes. Any questions, guys? Seem pretty
Yeah.
doable? Okay, so all these are is I have properties of matrices and scalar multiplication. So matrix addition is commutative. A plus B equals B plus A. Are real numbers addition commutative? Yep, I can switch it around, right? Okay, I can use the associative property under addition. So I have A plus the quantity B plus C, or that can be equal to adding A plus B, then adding C. Just like with addition of real numbers. The associative property of scalar multiplication. So it says I can multiply C times D. C and D, are they matrices or just numbers? They're just numbers, they're little, right? So I can multiply C times D and then times A, or I can take D times A then times C. This is a scalar multiplication. You do not see that of regular multiplication. You haven't done it yet, but you don't see it. Okay, scalar identity, the identity property. I can take 1 times A gives me A. 1 is a multiplicative identity, or scalar multiplicative identity. Isn't that the multiplicative identity of other numbers? When I multiply 1 by anything, I get the number. Distributive property of a scalar. So I have C times A plus B is equal to C times A plus C times B. Which one do you think you would do more, the left or the right?
The
Left. I would do the left. I'd add my matrices and then multiply by numbers. Because I always do better with smaller numbers, right? So what helps is if you get a problem like the right, can I write it like the left and do it? Yeah. Okay. And then it also works with the distributive property. It says, wait, it was distributive property twice, so it's just showing you twice. The first I distributed a scalar, then I'm distributing what on 6? A matrix. Okay. So you notice I didn't say multiplication. You guys don't know multiplication yet. We will do multiplication tomorrow. It is a process. A row times a column and add them. Row times a column and add them. You don't have to apply any of these if you don't want to, or you can use them to make the work simpler. Are we good? Riley, you good?
Mm-hmm.
Ryan? Okay. Okay, so if A is an n by n matrix and 0 is the n by n matrix, it's called the 0 matrix, and basically it just consists of all what? What do you think? Zeros. So if I take A times 0 or A plus 0, I'm going to get A, correct? Because 0 is the additive identity. Just telling you that. That's just telling you down here the additive identity, the 0 matrix. A 2 by 3 0 matrix has all zeros. A 0 matrix has all what? Zeros. That is it. Okay, so there'll be times they'll say A plus 0, and that's the 0 matrix. And so what are you just going to get? A. Really basic. There's a lot of definitions in here that you're like, duh. Okay, am I good? Okay, we'll go ahead and do this one since we're here, and then we're going to be done for the day. I thought we had some more examples, but okay. In order for matrix multiplication to occur, if I have A times B, A times B, and I have the order of the two, the columns of the first must equal the rows of the second. Columns in the first must equal the rows in the second. If that isn't true, you cannot multiply the two matrices. It is undefined. And what happens then, when I multiply an m by n and an n by p matrix, I get a m by p matrix. So I will let you write that down and we will stop for the day because I'm not going to go through those. I mean, I could, but I feel like. Oh, these notes didn't take very long. Okay, and then it just says matrix multiplication is a row by column multiplication. The entries in the row of the first matrix is multiplied by the columns in the second. And then you add them together. And it is a process that we will write out completely so you can see how it works because it's not just 6 times 3. Okay? It will take a minute. So I guess if you have this written down, we don't use it for examples and not.
Don't get rid of this.
What time is it?
9:30.
You guys can go ahead and get started. I'm not going to go